Have you ever had two music playlists and you decide that a couple of the songs in one playlist can be part of the other playlist? You select the songs and send them over to, let's say, your gym playlist. You have a party playlist, you like three songs there, you select them and send them over your gym playlist. The gym playlist, let's say, is sorted by song duration or length of the song. The other playlist is sorted by popularity. The algorithm select the songs and add them or merge them rightfully into your new playlist. How do you think the algorithm merges these two playlists? The songs from one playlist were sorted in one order, the song from the other playlist were sorted in another order. How does the algorithm does that? That is exactly the problem we're going to be solving today. So let's go ahead and jump into the code. Welcome back to another LeetCode problem solving video. I appreciate you for watching this video. Support me with a thumbs up, subscribe if you like the content. Let's go ahead and jump into the code. Welcome back everyone to another LeetCode problem solving video. Today I'm going to be solving merge two sorted lists. This problem is a linked list problem, and you can see that as soon as you open the problem because it's defining a list node for you here, or basically a node inside a linked list. And obviously it's important for us to know how linked lists work before solving this problem. I would definitely recommend knowing a little bit about pointers and nodes inside linked lists and how these things work, because even it's an easy problem, we're going to need to know a little bit about that to work with it, right? The problem says you're given two heads of two sorted linked list, list 1 and list 2. Merge the two lists into one sorted list. The list should be made by splicing together the nodes of the first two lists. Return the head of the merged linked list. Then we get a visual here of an example. Basically a list with, or linked list with 1, next 2, next 4. Then we get a second one with 1, next 3, next 4. Okay. After we merge these two sorted lists, we get 1 next, 2 next, 3, 4, and 4. Okay. I'm saying next because obviously you see this arrow here and it's not there without any reason. It's there because it's a pointer. It's a next pointer and it's contained by the node itself, right? By the previous node or the node in question pointing to the subsequent node, right? So we get an example here. It's basically the same one up here. The only thing I would mention here to clarify is that since we have two heads of two sorted list, okay? And then says return the head of the merged list. And we see that we get a whole list here, and then the output is not a head, it's the complete list. Okay, so again, this is why it's important to be familiar with linked list, because what it means by head, it's basically the head pointer that we can represent in many ways. For instance, in this case, we could say it could be 1, but also it could be another pointer sitting out here, or a dummy pointer that could be either pointing to this list, or it could be just created as a placeholder out here to merge these two lists. And we're going to see that once I start working into the problem. But again, these are things that are natural of linked lists, and it's important to know. So if you see this problem and you don't know linked list yet, I saw the problem before knowing about linked list. So I went and studied linked list, and then I came and solved the problem, or solved the problem anywhere else. I don't remember where, but it's out there. But anyways, let's go ahead and jump into constraints. And I want to make a quick pause here just to say, if you are the type of person who likes to solve problems on the go, meaning you're just on LeetCode grinding, trying to learn all the stuff, and you lack some foundation, and that's sometimes something that's very common, not only for self-taught people like me, but obviously for other CS students, right? I've confirmed this by talking to other people, interacting with them, and seeing that they also lack some foundation knowledge. So if that's the case, just try to be resourceful, try to find things out there that are good. I'm going to give you guys one resource that I've loved since I've been using it, and it's Algo Monster. It's not an ad. They're not paying me. I'm actually paying them to use their platform, but it's really good if you like to solve things on the go, because it goes deeper than just explaining the problem. It really helped me to understand things on a deeper level, because when it's trying to solve the problem, it gives you intuition, it gives you approaches, different walkthroughs, it gives you different solution implementations in different languages. Anyways, a lot of information about a particular problem, And I just really find it really helpful, and it would be a crime for me not to share that with you guys, especially if you're in your learning journey like me. Monster has really helped me. The only negative things I would say about Monster is that they don't have a lot of video solutions. And this is something that people have mentioned before, like, oh, they don't do video walkthroughs, whatever. They do have a YouTube channel with tons of videos and a huge amount of resources out there that are very good. They just don't do code walkthrough for all the problems on lead code, right? But I feel like there is enough of that out there. I mean, that's what we're doing, right? If you only learn through videos, maybe Monster's not for you, but I really, really recommend you giving Monster a chance, okay? Again, not an ad. It's just that it has worked for me tremendously, and, you know, we're getting better for interviews, but also it's important to have that foundation level. And that's what I like to explain things on real cases too, which we're going to see here. I'm going to go ahead and explain this problem with a real world case scenario where we can apply this problem so we see the real importance of it, right? So we see the examples here. Let's go ahead and jump into the constraints. And it says the number of nodes in both lists is in the range from 0 to 50, meaning the lists are going to have either no nodes, that's 0, or all the way up to 50, right? Anything on that range, 1 to 49, or no nodes, right? So the nodes values, meaning this 1, 2, and 4 here, could be anywhere from negative 100 all the way up to positive or 100, right? So that's that. The next thing would be that the both lists 1 and 2 are sorted in non-decreasing order, as we saw here. So obviously by the time of merge, we have to keep that order. Let's go ahead and jump into our board. And as I mentioned, I have one example here I'm going to walk through to explain the problem, basically the approach or doing a walkthrough, but also I want to take some time and explain a real case scenario where we can use this problem. That way we see probably more value in it, right? Okay, so imagine you have 2 playlists. These are musics, and you have 2 different music playlists on your app. And you've decided that there are, you know, you have a gym playlist and a party playlist, but you decided that 3 songs in your party playlist can be part of your gym playlist, okay? You say, you know, these songs are cool, or the BPMs are cool, I want them into my gym playlist, okay? So what happened is when you select the 3 songs to pass them over your gym playlist, look how you're sorting the music or the songs by duration or length of the song, right? So let's say this song is, you know, 1 minute long, this one's 2 minutes long, 3 minutes, 7 minutes, and so forth. Same thing here. They're sorted by duration, both playlists, and you decided to pass these songs. So you select your songs, and what basically happens in the back end is that a copy of the songs is created, because you're not deleting your playlist or the songs from the playlist. You're actually deciding to add them to the gym playlist. So what happened is that since you're sorting this, the algorithm implemented in the backend goes and look at these values, right? And we can say these are the values of our linked list, and these are in between them pointers, pointing to the next order, okay? To the next one. So the first song that's 1 minute long points to the next song that's 2 minutes long, and so forth, right? Same thing here. These are the values in our list, and they have pointers that are basically guiding us to the subsequent node. So the algorithm goes and look into them and says, you know, you're trying to move these songs. The algorithm obviously can do this, you know, simultaneously with multiple songs, but we're going to break it down into steps. So the first song is 2 minutes long. So the algorithm goes in here, check this value, and since we're merging an assorted number, we check the first node and the second node, and it says this node is greater than the first node, but it's equal to the second node. So let's go ahead and place it right here. So a new node is added to that list, and remember they are pointing to each other. All of them are pointing one to each other, okay? So the same thing happens for the third song you're trying to add. Basically, the algorithm goes and look, and it says, yes, are you greater than this? Yes, this, yes, and yes. So finally finds the spot and creates the pointer that points to it. And obviously for the last song, it goes and check and see if it's greater than all this, but it's not greater than this one. So it means it goes before. So that is how that playlist ends up getting organized or sorted by duration. So now your gym playlist has all the songs that you had before and now the 3 ones that you added from your playlist. So that's just a way to imagine how this type of functions would work. Obviously, you are sorting here more than anything, but imagining that you are sorting on a linked list, that these songs here are, notes in a linked list, that's how you would implement that. Okay, so let's go ahead and work now in a real example. Let's talk about how we would solve this with code, right? So we have 2 lists. This is basically the same example over here, but now we're gonna walk through it as we're solving the problem. The first thing we need to do, we have 2 lists and we have to merge them into one list, sorted, okay, keeping that order. The first thing we need to do, we're dealing with linked lists, so we're going to create something that's called a dummy node. And basically that dummy node at the beginning is not going to have any information. It's basically a placeholder that it's going to serve as, and I'm going to put it right here, merged list. It's going to be the head of the list we're going to be creating over here. Okay, so this node also has a value and a pointer. Okay, the value at this moment is, it's none, it's empty, right? I'm gonna just put it like that. There's no value in it, but it has a pointer, a next pointer, and no value. And it's what we call a dummy node, right? So let's go ahead and solve the problem. We're initiated our dummy node, and we're gonna basically walk through these values right here. The values are sorted, so we don't really have to worry about anything but comparing them, right? Because we have certain amount of nodes we can traverse, right? We can go from 0, basically no node, or from 1 to 50, right? And these nodes with pointers, remember these arrows here, these are pointers, these are next values, okay? Basically, we can check both values at the same time, okay? These 2 values and these 2 values, but we can check 2 values at the same time. So at some point in our iteration, we're gonna check, let's say, this value against this value, okay? The main idea here is that we can check 2 values at the same time, but the list is sorted. And since we're using a pointer here, since we're using the next pointer, we don't need a nested loop, okay? If we were dealing with 2 different arrays, maybe a nested loop would be the best way, but not even then, because we don't have to worry about sorting, right? So even then we can check both values at the same time and use pointers. So basically what I'm saying is, we can solve this in at least linear time because the list is sorted. That is a heavy load of work we don't have to do. We just have to worry about comparing these values and adding them to our merged list, okay? The trick part with this is using the pointers, the next pointers, to move around the linked list, traversing the linked list, okay? So the first thing we're going to do is basically start at both heads. These are heads of the linked list. So we're going to start at both heads, and we're going to say, is this value right here less or equal than this value? In this particular case, it is. So we can say, this dummy node now can hold the value of the list 1, or the smaller value. And I'm going to put that in green just in case. Perfect. Now we're pointing into our next node, but we have a head now. We have a value because we found the smaller node here. Well, what happened here next is that we still need to check this value, but since we found the smaller value up here, we're going to say to this node, let's go ahead and check the next node. And we're going to basically say the current value, which is this one right here, is going to be equal to the value in list 1, the smaller one, which is what we did. Now, the list.next, which is this pointer right here, is going to check for this value, okay? And that's when we compare these 2 values against each other. And that's the example I was mentioning. We can traverse this list at basically checking 2 numbers at the same time without having to incur in nested loops, okay? Cool. So now we do the same thing, same condition. Is this value right here less or equal than this value? When it's equal, so we can say, basically, go ahead and add this value right here. And, since we're checking the list 1 against the list 2, we went and added this value right here because it's less or equal, okay? So now, again, the same thing happens. We move into the third value, okay? The next pointer in list 1 move into the last value in the list. and checks for the same condition. Before I do that, let me not miss the next pointer right here, because every node has a next pointer, and that's something we have to definitely think about when solving this problem. So we're checking now 3 against 2, and we ask the same question: is this value less or equal? It is not. Okay, so what happens here? Well, finally, our value that's been sitting there for a while can come down here. So now our linked list is looking somewhere like this, or somewhat like this. But also, since we check this value, that value stays there. That pointer doesn't go anywhere. I mean, it can't go anywhere. We don't have either a next or a previous pointer here. It's not a double linked list. So that value is either going to crash your code, or it's going to be basically the end of the while loop we're going to be creating. But we're not there yet. Since this value went ahead and became part of our next node right here, we can safely say, you know, let's check this value, and let me go ahead and add my pointer over here, and this value obviously compares to this value, and 3 becomes the lesser value out of them two. So we go ahead and add it into our merge linked list like this, and get our pointer straight, and that's how that looks. And then obviously, since 3 was less than the value, we went through the list, okay, and we finally got rid of this pointer right here. You would say, yeah, but we still have 4 and 6. Perfect. Once we're done with one of the list, okay, we know that we reached the larger number on one of them. So what is left? Well, we have 2 values that are not part of our list. So we can just go ahead and send them into our list because they're already sorted. We went through one list by the time we finished this list, but now all we're left with, it's 2 last values, okay? So we can safely just go ahead and say, you know, anything that's left in that last list, you can safely add it to our merge list because they're sorted, okay? And that's something that definitely helps when solving these problems. So we can say 4 and 6. I hope that was clear enough. So this would be linear time if we can solve this, or basically it would be n times m, okay? The reason it is because we are basically traversing both lists at the same time, and that is obviously the length of the list 1 and the list 2 respectively. And we're going to see in code that the while loop continues until we reach the end of one of the input list, and during each iteration of the loop it processes one element, either from 1 or 2, list 1 or list 2. So in the worst case, if the loop runs for the combined length of both lists, we're going to have n plus m, or n plus m. Okay, so that's that. Let's go ahead and jump into the code and see how we can solve this. I'm going to expand that a little more. Perfect, because we have a long definition here. Okay, so first, there's something cool about linked list, and we can see the definition up here. Okay, we don't have to necessarily uncomment this, but I'm going to do it just so you have it there and we see how we can walk through this problem. But basically, it's the node with a value and the next pointer. Okay, we're going to create something that's called a sentinel node. Okay, and the sentinel node, it's basically the node that is going to hold the head of the merge list. The reason I'm going to do that is because it's asking to return the head of the linked list. So it's going to help us to return the head of the merge list without us having to use the current node. So we have a sentinel node that is initialized, you know, by our class definition up here. We're basically initializing a sentinel node, and then we're going to say, let's create the current node. And this is the node that is going to help us use or keep track of the end of the merge list. Okay, and then from here we have to iterate, right? So we're going to iterate over list 1 and list 2 at the same time. We can do that, and we're going to say if the list 1 value, okay, remember these are nodes that we have defined here. This is the definition of, we're calling the value right here. Okay, so if that value is less or equal than list 2 dot value, then let's go ahead and grab the current node pointer and let's set it to be equal to that value in the list node. Okay, so basically what we're saying here, oops, when doesn't go there. So we're saying basically we created a sentinel node. The sentinel node is going to hold the head of the merge list. The current node is going to help us to keep track of the end of the merge list. Okay, we iterate over both lists at the same time. We compare the values in both of the list. If the value in the list 1 is less than the value in the list 2, then the value in current.next, meaning the head of this pointer, becomes the value in list 1. Okay, basically we're appending the whole node, and we say, you know, list 1, it's equal to list 1.next. So now our list head becomes the next node. Okay, that is because we found the smaller or lesser value to be in this list. So we go ahead and increase that node next pointer to the next value. If not, then we say else, meaning the list 2 value is greater, then we can say current.next is going to be equal to list 2. So now we basically make that the second value, and we can safely say list 2 is going to be equal to list 2 next. Okay, we're basically comparing the two values. We're grabbing the smaller one and adding it to our head of our current node, and then we are making our actual node or actual head in list 1 the next value. We're checking different values using the next pointer, and I hope that's clear. But that's not it in this loop. Okay, every time we do that, then we also have to create the next node. Okay, current next. So we're basically saying, you know, since this value, this node got added right here or right here, then we need to move into the next node that this list has, because we need an empty spot basically to store the next value. Okay, perfect. So now let's say we reach the end of one of the list. If we reach the end of one of the list, we can safely get out of the while loop and say, well, current.next, the next pointer, all it needs is basically get the rest of the values. So the way is going to do that, meaning if the remaining nodes from one of the list is merged, then one of the lists is fully traversed. So just go ahead and append either list 1, we can say for shorthand, we can say list 1 if else list 2. And we're basically saying here, you know, let's say we added all the remaining nodes from list 1 or list 2. If one of the lists is fully traversed, which is what happened at the end of the problem, the example I was using, if one of the lists is fully explored, then go ahead and append to next either list 1 if it's list 1 or list 2. Okay, and here is, well, the sentinel node is going to help, because now we have to return the head of the node. So we're just going to say sentinel next. And this is cool here because we're calling the current node and we're initializing our node here. This is pointing to the head, and this keeps track of the end of the merge list basically, right? So basically every time we add one of the elements, we go ahead and make the current pointer next towards the end. Great. Once it's done, I'm going to submit, and we should be able to see our results. Great. It beats 100% just as 80% of the other solutions. Anyways, this was the problem of today. I hope you enjoyed. Give us a thumbs up if you like the video. Subscribe if you like the content we're making. We're out here getting better every day. I hope you can land that job. I'll see you in the next video. Thanks for watching.